Right then, this is the start of C4 and we're starting off by looking at atomic structure. And this is probably one of my favourite topics in science. So, we're going to start off by looking at the structure of an atom. Now, here we've got a scientist called Dalton, and he said that ancient Greeks used to believe that everything was made up of very small particles. He did some experiments in 1808 that proved this and called these particles atoms. Now, I'm mentioning the theory to start with because you may be asked to discuss how scientific theories come about, and really it's all about scientists coming up with an idea and then carrying out an experiment, gathering some evidence, using that evidence to support their theory or to adjust their theory. They negate it and then they say, actually this theory is not right, but this evidence shows that I can adjust this theory because this evidence has proved it. So please keep that in mind. So if we looked at the structure of an atom, then you will see that there are certain parts of it that you should know about. Okay, firstly, the centre, the nucleus, is where all of the mass is in an atom. Okay, and it's made up of neutrons and protons. Now, the first thing you need to know is that protons have a positive charge, okay, and they have a mass of 1. Neutrons, and don't get pulled into this by saying that neutrons are negative, because they are not. Neutrons are neutral. Okay, you can see that most of the word neutron spells out neutral. There is no charge. However, they do have a mass of 1, just the same as a proton, and that's why we get the whole mass. The atomic mass is just the number of protons and neutrons in the nucleus. And then on the outside you've got your electrons floating around, and they are negative, but their mass is so tiny that for this we just say that it's like nearly nothing. If we're looking at the mass of an atom, it's just the protons and the neutrons, and the electrons have a negative charge. So generally in most atoms, if you've got 2 positive protons, you'll have 2 negative electrons, because they'll attract to each other and keep it balanced. So as I said, here's a little diagram to show you the mass and the charge of protons, neutrons and electrons, and this is a common exam question where they ask you to fill it in, because they're just testing that you know that protons and neutrons have got mass but electrons haven't, that the charge of a proton is positive and that the charge of electron is negative, and there is nothing for a neutron. So if you looked, and please remember you've got your periodic table at the back of your exam paper, use it. There's also a key on there that tells you what all of these things mean. It actually tells you that the symbol in the middle is the symbol for that particular chemical. And while we're on that, please make sure it's capital letter, lowercase letter. If it's 2 together, 2 letters together, that means it is 1 element. If it's just a capital letter on its own, that's 1 element. Like a capital H would be hydrogen, and here you can see capital H little e together is 1 element, and that's helium. You'll see 2 numbers. Okay, the larger number is the mass number, and this is just all of the protons and the neutrons added together. And then at the bottom, this tells you, it's called the atomic number, but in brackets in the key at the back it does tell you that this is also the proton number. So this tells me that in this helium atom here, the mass in the centre, in the nucleus, is 4. I know that 2 of those 4 must be protons. So if I had 4, take away 2, that means that my mass of my neutrons must be 2. Then I can also use that proton number to work out how many electrons I've got, because if the protons are positive and the electrons are negative, then if there's 2 protons there must be 2 electrons. Okay, so here's some examples here. See if you can work out how many protons, neutrons and electrons there are. Now I'm just going to go through them because there's a couple on here that do catch people out. Hydrogen. You will notice hydrogen has a mass of 1, and it tells you that that 1 is a proton. So it means there are no neutrons. Okay, so there's 1 proton, no neutrons, and there is 1 electron, because if there's 1 positive, there's 1 negative. Boron, we've got 11 as the mass, so 5 of those are protons, so it means there must be 6 neutrons. And then lastly, if there's 5 positive protons, there must be 5 negative electrons. Oxygen, so there's 16 as the mass, 8 of those are protons, so that means 16 take away 8 means there must be 8 neutrons, and because there are 8 positive protons, there are 8 negative electrons. Sodium, 23 as the mass, 11 of them protons, so that means there must be 12 neutrons and there must be 11 electrons to balance out. Now this one, chlorine, on your periodic table it will say 35.5. If they want you to do anything with chlorine, they will write it in the exam question. Work with the one in the exam question. Okay, so we've got 35 as the mass, 17 of those are protons, so that means there must be 18 neutrons, and then there's 17 electrons. And then there's uranium. I'll leave you to work that one out. Okay, right, if we're looking at an isotope, now this is an exception to the rule that you normally come across. We do find that oxygen, carbon's another good example that comes up quite often. Sometimes you'll be given this and they'll say to you, okay, here is an isotope of oxygen, and you will notice straight away that the mass number is different in each one, but the proton number is the same. So just go with what you know. You know that the protons are all the same, so if the mass has changed, it means there must be more neutrons in the mass in each oxygen particle. You are just describing an isotope by saying that it's the same chemical with a different number of neutrons. Okay, so we've all got 8 protons, and there you go. Okay, right, electron structure. If we were looking at the electron structure, we could quite easily actually draw an electron structure. And if we looked at potassium, for instance, you will notice first of all the mass is 39. We're not worried about that for this. When we're looking at electrons, we know there's 19 protons, and because they're positive there must be 19 electrons. So the general rule is, if you've got 19 electrons, they have to go somewhere, and they go into these things called shells. And really the shell is just the pathway the electron travels in around the outside of the nucleus. The general rule is you have up to 2 electrons in the first shell, then up to 8 electrons in further shells. Okay, now so for instance on this example, potassium has got 19 electrons, so the inner shell must have 2 electrons. The next shell must have 8, because we've used up 2 out of our 19, so there were 17 left. So now we'll use up 8 of those, so that means now we've got 9 left. So we're going to fill up the next shell, and we're going to have 8 in there. So that means we've got 1 left over, because we've used up 18 so far, so that 1 must go in the shell on the outside. So if I was writing this as my electron structure, I would write 2, 8, 8, 1. You can draw it out like that if you want to, and that will be fine, but it's much quicker to just say 2, 8, 8, 1. Okay, please make sure you practice this because it comes up all the time. Okay, so you can see 2881. Now if we looked at the periodic table, there was a scientist called Mendeleev, and he actually is the person that's responsible for the periodic table, because he realised that all the different elements had certain properties in them that actually showed a pattern, and this is the best way anyone has ever come up with to arrange the different elements. Okay, so first of all, if you look, the vertical columns are called groups, and you will see that the horizontal rows are called periods. Okay, so if we have a look then, he noticed that elements in the same group have the same number of electrons in the outer shell, and this corresponds to their group number. So here you can see, for instance, group 1 over on the far left hand side, they all have 1 electron in their outer shell. Group 2 next to it has 2, and then if we go over to the far side, group 3, where you've got boron at the top, they all have 3 electrons in the outer shell. Then the group with carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7. And then if you look at the far right hand side where you've got helium, neon, argon, that's called either, some periodic tables call it group 0, because it's got a full outer shell of 8, which means they are not going to react with anything. They do not like it because they're all full up. So then if you looked at the periods, he noticed as you move down through the periods, an extra electron shell is added. So for instance, lithium that's in group 1, we know it's got 1 electron in its outer shell, and it's got 2 shells because it's in period 2, which goes across. If you look at sodium, sodium has got 1 electron in its outer shell, and it's in period 3 because it's got 3 shells, and so on. And you can see this was a brilliant little scheme that he came up with. And when he first came up with this, you can imagine there were actually gaps in the periodic table of elements that hadn't been found. So scientists got really excited and started going around trying to find these different elements. And at one stage, one scientist wrote to Mendeleev and said, I found an element and I think it goes in here, and here's my evidence. And actually, because of this system that Mendeleev had got, he said, well, I don't think your evidence is right. Do this experiment again, because I expect you to find this result. And when the scientists did do it, that is exactly what they found, because his system worked so well.